This lecture is on factoring polynomials. So, to start out with, what is factoring? What does that mean? Well, factoring is really just the reverse of multiplying two or more polynomials together. Instead of taking two or more polynomials and multiplying them to get one new polynomial, we'll go the opposite direction. We'll start with a particular polynomial and we'll try to break it down into a product of two or more polynomials. Typically we focus on factoring a polynomial completely, which means that we break it down into as simple pieces as we can. So factoring is basically taking a polynomial and rewriting it as a product of several factors. And these factors are polynomials themselves. So we usually factor polynomials completely, which means that we break them down into the simplest possible polynomials. In other words, none of the factors can be further broken down by factoring. Let's look at a few examples just to get a brief idea. We can look at this with numbers. Right, this is like factoring numbers into a product of prime numbers, for example. The idea is we're taking one composite thing and we're rewriting it as a product of sort of simplest forms that we possibly can. So for like a really simple example using numbers, right, if we had the number 18 and we wanted to factor it into prime numbers, we could write it as 3 times 6, for example. 3 is prime, but 6 is not. So we could take it one step further and write it as 3 times 2 times 3. We write 6 as 2 times 3. And that can be rewritten as 2 times 3 times 3 if we want to rewrite it in order, or 2 times 3 squared. That can't be broken down anymore. All of these are prime numbers, for example. So there's an example with numbers. But let's look at an example with polynomials in a particular way. So what's an example of a polynomial? For example, if you had this 10x squared minus 22x plus 4, you could rewrite this as x minus 2 times 10x minus 2. And what we're going to talk about in this lecture is how do you know that you can get from this part to that part? We could certainly check that this is true. We know how to multiply these two polynomials together, and if we multiply them together we would see that we would get this polynomial that we started with. But how do we figure out how to go the opposite direction? So that's what this lecture is going to be about. Okay, why are we interested in factoring polynomials? Well, there's several reasons. One reason, it often helps us to simplify things. So just like we sometimes simplify fractions by factoring numbers out of the top and the bottom of the fraction, we can do the same thing with polynomials that appear in the top and the bottom of a fraction. So for example, let's look at an example with regular numbers. For example, if we had 80 over 124, the way we try to simplify that is we would try to find out what are the common factors of the top and the bottom of this fraction. So for example, we know 80 can be written as 8 times 10, 124 could be written as 4 times 31. If we think about that for a bit, we would see that that's true. Then 8 I can factor even further. 8 I can write as 2 times 2 times 2. 10 I can write as 2 times 5. And then the bottom 4 I can write as 2 times 2. And then I've got the 31. And so what I'm able to do is I'm able to see, okay, because the factors of the top and the factors of the bottom share some 2's here, I can divide the top and the bottom by 2, or by 4 actually. And so if I divide the top by 4 and I divide the bottom by 4, these will cancel. This divided by 4 and this divided by 4 both equal 1. And so what I'll end up with is 2 times 2 times 5 over 31, which is 2 times 2 is 4 times 5 is 20. So I'll end up with 20 over 31. Now we don't usually quite write out all the steps and we're simplifying, but notice that what we're really doing is similar to what we're going to be doing when we factor polynomials. We break it down into fundamental pieces and then we cancel out things that we can see. The difference is with numbers, we're often able to see that we can divide by 4 without having to break it down completely in this complete way. But with polynomials, we're going to need to break it down that much. So for an example here, here's another example. That was example 1. Let's look at example 2 with some polynomials. So 10x squared minus 22x plus 4. If we had that over 8x to the 4th power minus 16x cubed minus 3x squared plus 6x, it actually turns out that I can rewrite the top as x minus 2 times 10x minus 2, and I can rewrite the bottom as x minus 2 times 8x squared minus 3 times x. And so this x minus 2 divided by x minus 2 is really just 1. So I can rewrite this whole thing as 10x minus 2 over 8x squared minus 3 times x. Notice that's much simpler. So the fact that I was able to factor here meant that I was able to take something that looked pretty complicated and rewrite it as something that looks much simpler. So that's one reason we may be interested in factoring. Another reason we may be interested in factoring is sometimes factoring can help us to solve certain types of equations. Polynomial equations, for example. Here's a usage we're going to see in a future lecture. So let's say, for example, that we have x squared minus 6x plus 8 equals 0, and we want to be able to solve for x. Well, what we've encountered before is we tend to just try to move things around. So we try to move x to one side of the equation by itself. The problem we encounter here is if we do that, we could try that. We could move the 8 over by subtracting it from both sides, and we'd get something like x squared minus 6x equals negative 8. But then it's very tricky. How do we get x by itself over here on the left-hand side? We've got an x squared, we've got an x. Those aren't like terms. We can't combine them. We could try taking the square roots, but then we'd have to take the square root of the whole side, and how do you take the square root of x squared minus 6x? That's not really going to cancel out the square on the x. It's very difficult to figure out how do we get x by itself here. And it turns out this is probably not going to help us. Well, it turns out what we can actually do is, one thing we can do is we can factor that. We can rewrite it as x minus 2, x minus 4. If we can figure out how to break this down, we can write it as its factors. And here we can see, well, if we're multiplying two things to get 0, we know that the only way to get 0 when you multiply is to multiply by 0. So this means that either this has to be 0, or this must be 0. One of these pieces must be 0. in order to get 0 when we multiply. So we can see in this case, now that we factor, we can see, okay, either we need x equal to 2, or we need x equal to 4. These are the only things that will make this product equal to 0. Those are the only things that will make this equation work. So we were able to solve that precisely because we could take this expression and rewrite it as its factors. We'll have a whole lecture later on where we talk precisely about how to do this. We can see that factoring in this case really helps us to solve a problem that it would be difficult to solve otherwise. So we're actually not going to try to factor every single kind of polynomial. We're going to restrict ourselves to certain cases in this class, and most of the classes that you might take after this are going to have similar cases. So let's talk a little bit about what kind of polynomials are we going to learn how to factor. Well, there are a few basic things. In this class, and in most classes that you're likely to take in the near future, we will factor polynomials over the integers only. So that means that we will only get integers as coefficients in our terms, right? This means that all the coefficients in our terms will be integers for now. So, for example, we're not going to get fractions. We're not going to get irrational numbers like e or things with square roots in them. We're not going to get imaginary numbers or complex numbers. It is possible to factor using these other types of numbers, but for this course we're not going to. So for example, you might have seen in another class that you could write x squared minus 2 as x plus the square root of 2, x minus the square root of 2. These are not integers. Right? These are actually irrational numbers. So while this isn't wrong, we don't need to do this in this class. If we see something that looks like that, and this is the only way it can be factored, we leave it this way. Because we can't factor it using integers, and we want integers. We want integers. Another example, if you see something like this, x squared plus 1, you might have seen in another class that you can write this as x plus the imaginary number I times x minus the imaginary number I. Again, these are not integers. These are imaginary numbers. So in this class, we're going to leave this alone. We're not going to factor it. It's not wrong to factor it, but since we're limiting ourselves to only factoring it over integers, we can't do it over the integers because these aren't integers. So we would stop at this point. If you've never seen any of these examples, you don't need to worry about it. You can just put this out of your mind and just know that when we factor, you just need to be sure that what you're doing makes sense in terms of getting integers as part of your coefficients. Okay. So how do we factor polynomials? Well, we could do this by trial and error. Right? We could just try out a bunch of things. If we have a polynomial, we could guess. We could think, okay, maybe we could break it up into this factor. and that factor. And we could just try it out and see how close we get. And if that doesn't work, we could try modifying it a little bit, try again. That's actually one thing you can definitely do when you try to factor things. You can always try to do trial and error. But that may be sort of time consuming, it may be sort of difficult. So another option and one that I think is probably better is we can look for patterns when we multiply polynomials. And once we recognize those patterns, we can then employ them in the opposite direction. If we multiply a bunch of different things together and see what the patterns are, then we can identify polynomials that fit those patterns when we want to factor. We can use these patterns to identify polynomials that can be factored in a particular way. Okay, so if we're going to do that, let's look for patterns when we multiply polynomials. Now, another quick note about the kinds of things that we're going to factor. Almost everything we will have to factor in this class will be a product of either a monomial with some other polynomial or binomials. So let's just do a short definition again. We've already used these words, but let's actually write them down formally. Right. A monomial is polynomial with one term. So for example, things like 3 x squared y, negative 21 a to the 4th power, 47 a squared b to the 3rd power. For example, these are all monomials. A binomial is a polynomial with two terms. Right. We see the word bi. Mono tends to mean one. Think of monocle. Binomial, think of bicycle. And you can guess also that trinomial tri for 3, tricycle for example, or triangle, is a polynomial with 3 terms. So of course, again, if we want to do some examples of binomials would be x minus y, x squared plus 6, 3ab minus b squared. These are all binomials. Trinomials, x squared plus 2x minus 9 is one example. A squared minus 2ab plus 3b squared, for example, is another trinomial. Each of those have 3 terms. Okay, so these are just some definitions that are important because when we use the words, you want to know what we're referring to. Every time we say monomial, we just mean a polynomial with a single term. Every time we say binomial, we just mean a polynomial with 2 terms. So most of the stuff we're going to be multiplying in this class, and most of the stuff we're going to be factoring in this class, will be a product of a few things. A monomial and another polynomial, and often two binomials. We will occasionally factor things that are the products of a binomial with a trinomial or other types of patterns, but overwhelmingly, pretty much everything we're going to need to factor for now is going to be one of these two things. So for now, you just want to be on the lookout for when can you pull a monomial out of the thing you're trying to factor, and when can you break it down into a product of binomials. You'll see that pattern as we move on. So let's try multiplying monomials by polynomials and look for patterns that would help us to go backwards when factoring. And then let's multiply binomials together and see what the patterns are. And then see if that helps us to identify patterns we can use to go backwards when factoring. So the simplest possible multiplication is by a monomial. Let's look for patterns. What might they be? Well, let's start out by looking at some examples here. So for example, let's try 3x, that's a monomial, times x squared minus 2x plus 1. Well, we know how to multiply this out. We just kind of use the distributive property here. So again, I'm going to start by writing everything out as addition. 3x times x squared plus negative 2x plus 1, and I'm going to use the distributive property. And so I'm going to get 3x times x squared plus 3x times negative 2x, 3x times 1. And then when I do that, I can reorder things so I get 3x cubed. I can say 3 times negative 2, which is negative 6. X times x is x squared. And here 3x times 1 is just 3x. So when I've rewritten it, I've ended up with this. Which of course, again, you can write it as minus 6x squared as well, as if you prefer. Let's look at another example. Another example, x squared minus y squared times 3xy cubed. Again, this is a monomial. It's a more complicated looking monomial, but it only has one term. So again, I'm going to start by rewriting everything as addition, x squared plus negative y squared times 3xy cubed. And then I'm going to use the distributive property, as I know how to do. So I will get x squared times 3xy cubed plus negative y squared times 3xy cubed. And then I'm going to go ahead and simplify each piece. I have 3, and then I have x squared times x, so that's x cubed. And then I have y cubed, that hasn't changed. And here I have a negative y squared, so it's really like having a negative 1 there. Negative 1 times 3 is negative 3. And then I have just a single x, and then I have y squared times y cubed, so that would be y to the 5th. So again, that would be my simplified version. So what pattern did I notice here? And this is for factoring out a monomial. Well, notice that if I have something where I can pull the same thing out of every single piece, then I can go back to the form with a monomial. Notice here in this first example, I can pull a 3x out of every single piece. This is divisible by 3, this is divisible by 3, this is divisible by 3. So I know I can pull a 3 out. And then this is divisible by x, this is divisible by x, and this is divisible by x. So I know I can pull an x out. So all I have to do in order to factor this is to figure out, once I pull a 3x out of each piece, what's left. Well, this first piece, if I divide it by 3x and put it out here up front, I have an x squared left. This second piece, if I pull out a 3x and put it out front, I still have a negative 2x left over. And this last piece, if I pull out a 3x out, what do I have left? Well, when I say pull out, I mean divide. So if I divide 3x by 3x, what I have left is a 1. So I've just gone backwards. I've just gone right back to the expression with which I started. I can do the same thing at the bottom. I can look for what does each term have in common. Well, again, they're both divisible by 3, so I know I can pull a 3 out. I can divide each piece by 3. This part is divisible by x, and this part is also divisible by x, so I know I'll be able to pull a single x out. And then this part is actually divisible by y cubed, and this part is also divisible by y cubed. So I know that I can pull a y cubed out. So what happens when I've pulled those things out when I've divided each piece? Well, this first piece, if I divide by 3x y cubed, I have an x squared left. This second piece, if I divide by 3, I still have a negative 1 left, so I have to keep that negative sign. The x divided by x gives me 1, so that cancels. And the y to the 5th divided by y cubed leaves me with the y squared. So you'll notice, here's what I'm left with. So, what's the pattern? I just need to find the biggest thing that divides evenly into every single term. We call that, this biggest thing, the greatest common factor. And so if we wanted to write it formally, if we have some expression that can be written as a times some stuff plus a times some more stuff plus a times some more stuff and so forth, I'm just calling that other stuff b. A times b to the n. These are each different bits of things. I know that I can rewrite this as a times b1 plus b2 plus b3 plus bn. The basic idea is I can divide every single piece by a, and then write the thing that I've divided by, that greatest common factor, out here. See, here we've divide each piece by the greatest common factor, which we often abbreviate as GCF, which is a in this case. Right? And then that greatest common factor goes out here. So I want to write a little note here. Since looking for a greatest common factor is one of the easiest things to do, as we'll see, whenever we have a polynomial to factor, it makes sense to try this first. It's possible there may be no greatest common factor, so then we can't use it in those cases. Or it may be that once we pull out a greatest common factor, we'll still need to keep factoring further. But if we go ahead and pull out any greatest common factors first, that can be helpful because it can simplify things if we need to do further factoring, and it's one of the easiest things to do, so why not? Why not try it first? So I would say Look for a greatest common factor first is a good tip. Okay, so we've explored the pattern about what happens when we multiply a polynomial by a monomial. The next case is when we multiply two binomials together. So let's look for those patterns. So let's look at some examples. We'll do 3 examples, and then we'll take a moment to explore each of those patterns. So, here's our first example. Let's look at x squared plus 5 times 2x minus 1. Each of these are binomials because they each have 2 terms. Okay, so the way I would go ahead and multiply these is I'd start by changing everything to addition. So I'll write the 2x minus 1 as 2x plus negative 1 because I like to do that. And then I'll go ahead and use my distributive property. So I'm going to take the x squared and multiply it times 2x plus 1. And then I'm going to take 5 and I'm going to multiply it times 2x plus 1. Notice you can use the distributive property in the direction. I'm going to do it this direction for now. X squared times 2x plus negative 1 plus 5 times 2x plus negative 1. Okay, and then I continue my distributive property here by distributing the x squared to each piece and the 5 to each piece. And so what I get is x squared times 2x plus x squared times negative 1. Again, I want to be careful not to lose that negative sign. Plus 5 times 2x plus 5 times negative 1. And so what I get when I simplify all of that, x squared times 2x is 2x cubed. X squared times negative 1 is negative x squared. 5 times 2x is 10x. And 5 times negative 1 is negative 5. So I can write it like this, or if I prefer, I can go back and turn all of the plus negatives into subtraction. Either way is fine. So that's one example. Let's do another example. I've got 3x minus 1 times 2x plus 5. And again, I'm going to do this in a similar way. I'll go ahead and rewrite everything as addition. 3x plus negative 1 times 2x plus 5. And then I'll go ahead and distribute things. So let me go ahead and take this 2x plus 5 and distribute it to each piece. So I'll get 3x times 2x plus 5 plus negative 1 times 2x plus 5. And then I'll distribute the 3x to each piece and the negative 1 to each piece here. So we'll get 3x times 2x plus 3x times 5 plus negative 1 times 2x plus negative 1 times 5. 3x times 2x is going to be 6x squared. 3x times 5 is going to be 15x. Negative 1 times 2x is going to be negative 2x. And negative 1 times 5 is going to be negative 5. Now I notice that the 15x and the negative 2x are like terms, so those can be combined. So in this case I'll actually get 6x squared. 15x plus negative 2x is going to be 13x, and then I'll have a plus negative 5. Again, I could rewrite the plus negative 5 as minus 5. That would be okay also. Let's do one more example, so we'll have several patterns to look at. Let's look at a plus b times a minus b. Again, I'm going to change that to everything to addition, so I get a plus b times a plus negative b. And then I'm going to distribute, use the distributive property. So let's take a plus negative b and distribute it to each piece. Or I could have distributed a plus b to each piece in the second one, doesn't matter. So let's get a times a plus negative b plus b times a plus negative b. And then I need to do the second step of distributing. So I'll say A gets distributed to each piece here, and B gets distributed to each piece here. So I get A times A plus A times negative B plus B times A plus B times negative B. And so that simplifies to A squared plus negative AB plus, we can write BA as AB if we want to write it alphabetically, which is nice because it helps us keep track, plus negative B squared. And you'll notice these two are like terms. They both have an AB in them as the variable part. But negative AB plus AB is just going to be equal to 0. So what we're going to get here is going to be A squared plus 0 plus negative B squared, which we can rewrite as A squared plus negative B squared, or as A squared minus B squared, if we prefer. Okay, so we've looked at 3 examples. We already know how to do this multiplication, but the reason I've written out all the steps of the multiplication is we want to stop and we want to look for patterns. So let's look at example 1 first. We want to think about how could we take this example and go backwards. We want to start with this and end up with this. So how can we look at that and figure out how we can start with the n polynomial and go backwards to the factors? So we got to look for the pattern. Well, if we look at the pattern here, let's think about trying to do the same math steps we did for multiplying, but work backwards. So, how can we go from this step to this step to this step, which would take us back to what we started with? Well, we may notice that what we need to do is, if we group everything into 2 sets of terms here, right? If we group these 2 things together, and we group these 2 things together, then we may notice we can factor out something common here. Notice, to get to this step here, I need to be able to pull an x squared out of these first 2 terms. And to get to this step here, the second part, I need to be able to pull a 5 out of the last 2 terms. So if we just group these 2 terms together, we can look for the greatest common factor, which is 5. And if we group these 2 terms together, we can look for the greatest common factor, which is x squared. If we then do that, if we group these first 2 terms and the last 2 terms together, you see we can get to this step, where we can factor the greatest common factor out of each piece. And as soon as we factor the greatest common factor out of each piece, to get from this step back to that step, all we have to do is treat the 2x plus negative 1 as the variable part and add these 2 coefficients to get back to this step here. So let's write out more clearly what we just noticed as a pattern. What was the pattern there? Let's get a fresh page. To go backwards and factor, we need to group together the first 2 terms and the last 2 terms. We then factor out the greatest common factor from each group. And then finally, we can then treat these 2 greatest common factors as coefficients and combine them into a single binomial coefficient. So this particular pattern that we're noticing, we call this pattern factoring by grouping, because that's particularly what we do. We group two of the terms together and the other two terms together, then we pull out the greatest common factor, and then we combine those two pieces. So let's look at some examples to see how we actually do this when we haven't seen the multiplication happen. So for example, let's look at this one. 2a cubed minus a squared plus 2a minus 1. And let's see if we can do this. So again, just like in every other problem, I'm going to start out by rewriting everything as addition. So I'm going to write this as 2a cubed plus negative a squared plus 2a plus negative 1. As I've said before, I like to do that just to be sure that we never lose track of where our negative signs belong. Okay, now that I've done that, I'm going to try this grouping business. I'm going to go ahead and I'm going to try grouping the first two together and the last two together and see, can I get a greatest common factor out of each piece? And when I do that, do I end up with the same variable part left over in the parentheses? So let's try this. If I group them together, I can see what is the greatest common factor here. The greatest common factor of this piece is going to be a squared. And what's the greatest common factor of this piece? Well, I don't see one, so it would have to be 1 if it works. So let's see if that works. Let's try it. Let's try rewriting it. So if I rewrite it this way, I would get an a squared. I'd divide each piece by a squared and then put an a squared on the outside. So 2a cubed divided by a squared, right, plus negative a squared divided by a squared. And I can do the same thing here. I can pull out a 1. Well, pulling out a 1 doesn't really do anything, so I'm really just writing it there. And so of course what happens here, so I get a squared times 2a plus negative 1 plus 1 times 2a plus negative 1. Is my variable part the same in each example? It is. These are the same. So I can treat these two pieces as my coefficients and add them together. So I get a squared plus 1 times my variable part. My variable part is 2a plus negative 1. So I've factored it. I have written it as the product of two polynomials. I did that by grouping. Let's look at another example. So in this example, we have x cubed minus y squared minus x squared y plus xy. So again, just like before, I'm going to start by rewriting everything as addition to begin with. So I'm going to write this as x cubed plus negative y squared plus negative x squared y plus xy. Okay, let me see if I can try grouping these together and see if I can pull out a greatest common factor. So let's try grouping these two together and these two together and see what happens. So if I do that, what's the greatest common factor here? Well, it's just 1. I don't have any other factors. Let's see if we can find a greatest common factor here. The greatest common factor here would be xy. So let's give it a shot and see if that works. So in this first case, the greatest common factor is 1. I can write a 1 out front without having to pull anything out, because 1 times everything is just itself, more or less. Okay, in the second case, I want to divide each piece by xy. So if I divide the first piece by x, so let's put an xy out front. If I divide the first piece by xy, I would get a negative x left over. If I divide the second piece by xy, I get a 1 left over. Okay, so I was able to factor each piece. Now I need to double check, is the variable part the same? Ah, these are not the same at all. I've got very different variable parts. These are not equal. So I don't have the same variable part. So what do I do in this case? It didn't work. I tried to group stuff and factor it, and it didn't work. Well, one thing I should consider in this case is maybe the order in which this original problem was written isn't the order I need in order to group things. I grouped the first two pieces together and the last two pieces together, but maybe I should have grouped the first and the third piece together, or the first and the fourth piece together. So let me try a different order. This grouping didn't work. So let's reorder and try a different grouping. So I'm going to reorder this. There are a bunch of different ways I could try it. I could try doing x cubed plus negative x squared plus y plus negative y squared plus xy, or I could throw the y squared here to the end. Doesn't really matter what we try. We just want to keep trying new things if we can't get it to work until we're sure we've tried all the possible groupings. So let's go ahead and try here. Let's write it as x cubed plus negative x squared y plus xy plus negative y squared. That's a reasonable order too, because we've got everything with an x in it coming first. It's in order of the powers, the degrees of the x's. We've got x cubed in the first term, x squared in the next term, x in the next term, and no x in the final term. So that might be a good thing to try. So let's try that out. Let's see if grouping now, in this case, works. If I group the first two terms together and the last two terms together. Alright, so what is the greatest common factor here? In this case it would be x squared. What's the greatest common factor here? In this case it would be y. So let's try doing that. If I pull an x squared out of this first group of two terms, x cubed minus x squared is just x. Negative x squared y divided by x squared is going to be a negative y. Okay, now in the second grouping, if I pull a y out front, I have to divide each piece by y. So xy divided by y is just x. And negative y squared divided by y is just negative y. So again, I want to check, is the variable part the same? Yes, the variable part here is the same. So that's exactly what I need in order to do factoring by grouping. Now I can simply add these two coefficients. So I can say x squared plus y times the variable part, which is x plus negative y. And again, I have managed to factor it. Notice the only difference in this second example is that the first grouping I tried didn't work. When you want to try factoring by grouping, you can try factoring it in the original order, but there may be some times when you want to try rearranging the order a little bit to see if rearranging it makes the grouping work. Notice this whole technique fails if I don't get the same variable part here. I have to have the same variable part. Because if it's not the same variable part, then I can't, these aren't like terms, and I can't combine these coefficients. So if I get something where the variable part is not the same, I should stop and try a different grouping. Okay. So one thing we've noticed there, one thing you may have noticed over these last two pages, when we have four terms, factoring by grouping is a logical thing to try. actually, factoring by grouping will work if you have 6 terms or 8 terms in many cases. It would even work in certain cases where you had multiples of 3 terms or multiples of other numbers of terms. You could try this out by testing it. Instead of multiplying 2 polynomials together, you could try multiplying 2 trinomials or a binomial and a trinomial. You'll see in those cases too you could employ a certain kind of factoring by grouping. In this class though, you'll notice for the most part when we see factoring by grouping though, we're really just trying to get back to 2 binomials. Since most of what we try to factor is a product of 2 binomials, we can pretty much just restrict ourselves to the case where we have 4 terms. But if you're curious about how factoring by grouping really works, you could try playing around with multiplying bigger polynomials. And you notice that there's actually a larger pattern here. It works for binomials, it works for trinomials, it works for combinations of different types of polynomials that have been multiplied together. But for now, if you ever see 4 terms in the thing you need to factor, factoring by grouping is a logical thing to try after you've checked for any common denominators, because factoring by grouping precisely involves grouping 2 terms together and another 2 terms together, and then trying to pull out the greatest common factor. So if you've got 4 terms, it looks like that sort of approach might work well. Okay, now let's think about what happened to the pattern in example 2. We'll start a fresh page for that. This was similar to the pattern in example 1, except you'll remember that we ended up with a couple of like terms that we were able to put together. So let's review. What did example 2 look like again? Here's what it looked like. We had 3x minus 1 times 2x plus 5. We rewrote everything as addition. And then we did our distributive property, 3x times 2x plus 5 plus negative 1 times 2x plus 5. And then we multiplied each piece, 3x times 2x plus 3x times 5 plus negative 1 times 2x plus negative 1 times 5. And we multiplied all of these individual pieces together. We got 6x squared plus 15x plus negative 2x plus negative 5. And then all of this looks like example 1 until we hit this point. Here is the step where it starts to differ from example 1. In example 1 we didn't have any like terms. But in this example what happens is these 2 middle terms are like terms, so we can add them together. So we end up getting 6x squared plus 13x plus negative 5. So instead of 4 terms, now we have 3 terms. We end up with a trinomial. Precisely because we had these like terms up here that could be combined. So we notice that this part here came from the sum of 2 like terms. So if we want to go backwards in this case, if we want to start from this step and end up back to this step, we have to figure out how can we break this 13x up into these 2 pieces. How do we figure out what those 2 like terms were? Because notice, if we can get from this step to this step, all of this is just factoring by grouping, which we already know how to do. So it seems that the trick here, the one extra step that we need in order to factor things, like what we get here in example 2, is we need to figure out how do we break up this middle piece. So let's think about this. I'm going to write it even more generally here. We have a polynomial of the form ax squared plus bx plus c. Right? Well, remember, since we're only looking at polynomials over the integers, a, b, and c have to be integers. So what we need is, we need to find a way to rewrite the bx part as the sum of two terms. And we need to be able to pick those terms precisely so that we can factor by grouping. So, how do we find these two pieces? Let's open up that question on a new page. Well, it might be helpful to think about generally what happens when we multiply stuff that looks like this. This can be a little bit harder to follow because it's abstract, but let's just take a moment to play around with it to see if it helps us. Let's think about the general form we have when we multiply two binomials like the ones in example 2. So we could write the general form this way. Let's pick capital A, B, C, and D as integers. In math, usually when we use a capital letter, it's not the same as a lowercase letter. So just a little note. In math, lowercase a is not the same thing as uppercase a, for example. Just a little side note. So, if I want to write out a general form, here's how I might write it. Capital AX plus B, capital B, times capital CX plus D. Okay, so A, B, C, and D, they can be positive, they can be negative, any kind of numbers. They can even be stuff that doesn't have numbers in it. It could be variables or something. But this is two binomials where I'm multiplying, and they each have an x in one part of the term, one of the terms. So let's go ahead and multiply this out the way we usually do. So first we'll distribute the cx plus d to each piece on the left, so ax times cx plus d plus b times cx plus d. Now I'll distribute the ax and the b. So I'll get ax times cx plus ax times d plus b times cx plus b times d. And now if I simplify, I get acx squared plus adx plus bcx plus bd. And you'll notice the same pattern. This is what we're trying to figure out. These two are like terms here, so we're going to have to add them together. So what we'd get is ac times x squared plus ad plus bc, we add the two coefficients, times x plus bd. So the idea is, if we're presented with a polynomial that looks like this, we need to figure out, this is our b here, that's our b, our lowercase b. We need to figure out how to break our lowercase b into these two parts, the AD part and the BC part. How on earth can we figure that out? Well, in order to be able to figure out what the pattern is, I'm going to point out something. So in this example, our capital AC is equal to lowercase a. Remember, we had things written out as lowercase ax squared plus lowercase bx plus c. That was our general form. So in this example, our capital A, capital C is equal to our lowercase a. That's the coefficient on the x squared. Our coefficient on the x is this capital AD plus capital BC. So we can see clearly where the two parts are. And this BD here is our lowercase c. So we'll notice in this case, lowercase a times lowercase c is capital A, capital C times capital B, capital D. Well, that's actually the same thing as AD times BC. And notice the B that we're trying to break up is AD plus BC. So we notice these are the two pieces we're looking for. And notice the two pieces we are looking for, in order for them to work, they need to add up to B, but they also need to multiply to get AC, right? Because the pieces we're seeking are these two pieces here, and if we can find them, they add up to B, and they multiply to give us AC, no matter what that A and that lowercase a and that lowercase c are. So, what's the pattern here? Let's write it out. If we are trying to factor a polynomial of the form ax squared plus bx plus c, and of course remember that a, b, and c here are integers, then all we need to do is to find two numbers that add up to B and multiply to get A times C. Then we can rewrite Bx as the sum of these two coefficients, and we can factor by grouping. This is the pattern. Let's try some examples where we actually do this. These are examples where we want to break Bx into two pieces and then factor by grouping. So we'll start with our first example here. Let's look at x squared minus x minus 72. So first of all, I'm going to rewrite that, or I'm going to say 1x squared, because I want to make sure everything has a clear coefficient. If there's no coefficient, it's clearly 1, because 1 is the only thing you can multiply by x squared to get just x squared, plus negative 1x, because that's negative, and so we have to have a negative 1 out front, plus negative 72. All right, so let's see if we can figure out how to factor this expression. We know from what we've just talked about that the way to factor this is we need to be able to break this negative 1x into two pieces somehow. And so the way we do that is by recognizing how well this fits the pattern ax squared plus bx plus c. Well, we have in this example our a is 1 because that's a coefficient of x squared. Our b is negative 1 because that's a coefficient of x. And our c is negative 72 because that's the term that has no x's in it. So what we need to do is we remember we need to find two numbers that add up to b. So our b in this case is negative 1, and multiply to get a times c. Well, in this case, a times c is 1 times negative 72, so that's just negative 72. So we need them to add to negative 1, multiply to negative 72. All right, so how do we do that? Well, the simplest thing to do is figure out what are all the pairs of numbers that multiply to get 72. Right, so what pairs of numbers can we multiply to get negative 72? Now, you may be able to see this without writing them all out, but because we're going to do this example really simply and clearly, I'm going to write out all the possibilities, and then we'll pick the one that works. So the things that multiply to get negative 72. Let's start from the lowest numbers and work our way up. So 2 obviously goes in, it's an even number, but because 72 is negative, we could multiply one negative and one positive. So we could multiply 2 times 36, negative 36 to get negative 72, or we could do negative 2 times positive 36 to get negative 72. It looks like 3 goes in also. In fact, 3 times 24 equals 72, so 3 times negative 24 equals negative 72, or negative 3 times 24 will give us negative 72. Looks like 4 also goes in. In fact, 4 times 18 is 72. You can check that. So 4 times negative 18 will be negative 72, or negative 4 times positive 18 is negative 72. Then it looks like 6 goes in as well. So 6 times 12 is 72. So 6 times negative 12 is negative 72, or negative 6 times 12 is negative 72. And finally, 8 times 9 is 72. So we can say 8 times negative 9 is negative 72, or negative 8 times 9 is 72. So we have 1, 2, 3, 4, 5 twice, so we have 10 different pairs of numbers that multiply to get 72. One of those has to add up to equal negative 1. We can rule off pretty quickly all of these ones here. These are not going to add up to be negative 1. Those are not going to add up to negative 1. These are not going to add up to negative 1. They're too far apart, too far apart. Aha! But the 8 and the 9 are hopeful. They're 1 apart, and they have opposite signs. So when we add them, we can see that 8 plus negative 9 is going to give us negative 1. So we can see we have 8 plus negative 9 equals negative 1, and 8 times negative 9 equals negative 72. So this is what we want. We know now that we can take our 1x squared plus negative 1x plus negative 72, and we can break this piece into something that has an 8 plus negative 9x in it. So this will be x squared plus 8x plus negative 9x plus negative 72. Now we've got our 4 pieces. We can factor by grouping. We just group the first 2 together, and we group the last 2 together. We see what's the greatest common factor. Well, here it's just x. What's here the greatest common factor? We can see here it'd be nice to actually take a negative sign out because they're both negative, and a 9. So what we're going to get here, we're going to pull an x out. X squared divided by x is just x. 8x divided by x is just 8. And here, if we pull it on negative 9, we get negative 9x divided by negative 9 is just x, and negative 72 divided by negative 9 is just 8. Aha! Now we can see that in fact these 2 variable parts, these are equal, which is what we need. So we can just add these two coefficients. So we get x plus -9 times x plus 8. And we have factored this expression. Now, you probably actually could have done this more quickly, because if you just thought about what factors you know of -72, you might have immediately been able to come up with, 8 and 9, where one of them is negative would work, and 8 and 9 are 1 apart, so you could get the -1. So you may not actually need to write out all of these steps. But if you're not sure, if you can't see it right away, if you write out all of the possible factors, you can always march through and find the one that adds up to what you need. Let's try another example. In this example, we have 12x squared minus 19x minus 18. Now, I may notice something right away. These numbers are all pretty big. I might want to check and see, do they have a common factor that I can pull out to start with? So I want to double check and see, is there anything that goes into 12 and 19 and 18? Well, in this case, it doesn't work, because there are things that will go into 12 and 18, but not 19, because 19 is actually a prime number. But it's good to check. Whenever we see larger numbers, we might save ourselves some trouble if we first look to see if they have a common factor. Okay, I'm going to rewrite this as addition, as I always do. 12x squared plus -19x plus -18. And here I'm going to notice that this, in fact, has the form ax squared plus bx plus c, right? In this example, a is 12, b is -19, and c is -18. So, I need to find two numbers that add up to -19 and multiply to get, what is a times c? 12 times -18. So, what is 12 times -18? Well, it may take me a minute to go ahead and multiply that out. If I do, I'll find I get 216. So I need numbers that add up to -19 and multiply to get 216. So I could start by looking for factors of 216. Sorry, -216. -216. So I can start by looking for factors of 216. Because this is a relatively big number, it might take me a while. For example, I notice it's an even number, so 2 goes into it. So in fact, 2 times 108 will work. But you notice 2 and 108 are so far apart, you're not going to be able to add them together to get -19. We'd have to have -2 and +108, so when we add them together, we're actually going to be finding the difference because they'll have opposite signs. They're not going to be 19 apart. So I might want to try starting with my guesses with even larger numbers. It looks like 4 goes into 216. 4 goes into 216 54 times. Well, 4 and 54 are still 50 spots apart, so that's not quite close enough. So I probably want something even bigger than 4. I could ask myself if 8 goes in. I might try that. And in fact, if I try it out, I'll see 8 and 27 work. So that seems closer. Let me write that down as a possibility. If I have -8 times 27, or 8 times -27, I'll see, now, are 27 and 8, when I add them together, will I get -19? It looks like they might. 27 and -8, I will get 19 is the answer. But that's positive. I don't want positive, I want -19. But I'll notice that 8 plus -27, that does, in fact, give me -19. So I've found my two terms. I can see that 8 plus -27 equals 19, and 8 times -27 equals -216. So I know that 8 and -27 are the two pieces that I want. Once I've figured that out, even though this is a pretty big problem, I can go ahead and do it because I know that I have 12x squared plus -19x plus negative 18, and then I can take this negative 19x and rewrite it as a sum. I can break this into 8 plus negative 27 times x. And once I've done that, so I have 12x squared plus 8x plus negative 27x plus negative 18. Now I can go ahead and do factoring by grouping. I group the first two together, I group the last two together. I find out what is the greatest common factor. Well, the greatest common factor here is 4x. And the greatest common factor here, again, I probably want to pull out a negative sign here, so I get negative 9. So let's try that. So I pull out my 4x. 12x squared divided by 4x is 3x. 8x divided by 4x is 2. Negative 9 is what I've pulled out, so negative 27x divided by 9 is 3x, and negative 18 divided by 9 is 2. I want to double check that my two variable parts are the same, and in fact they are. They're equal, which is what I need. So I can go ahead and combine these like terms by adding the two coefficients. So I get 4x plus negative 9 times 3x plus 2. So now that we've seen a couple of these examples, I want to summarize in a note here. We notice when we have something of the form ax squared plus bx plus c, or something that can be written in that form, it makes sense to try this method. And we call this method the AC method. Not everybody uses that same term, but that's kind of the technique we're doing. We're multiplying A times C and using that to help us figure out how to break up the B part. Okay. Finally, let's look at example 3. So we'll remind ourselves what example 3 looked like. Example 3 was this, a plus b times a minus b. So again, I'll go ahead and rewrite that as a plus b times a plus negative b. And then I'll go ahead and do the multiplication to remind ourselves what that looked like. So we have a times a plus negative b plus b times a plus negative b. We distribute that a plus negative b to each piece. Now I want to distribute the a to each piece here and the b to each piece here. So I get a times a plus a times negative b plus b times a plus b times negative b. And multiplying everything out there, I get a squared plus negative ab plus ab plus negative b squared, just by simplifying and writing everything alphabetically when I can in the same term. Now again, you may notice here, negative ab and ab are like terms, but they're going to add together to give us 0. So what we're going to end up with here is a squared plus 0 plus negative b squared, or in other words, a squared plus negative b squared, which we can also write as a squared minus b squared. So what pattern did we notice here? Well, we notice when we have a difference of squares, in other words, something of the form a squared minus b squared, we can rewrite it as the product of a sum and a difference. Like this. A squared minus b squared is going to be a plus b times a minus b. Whatever we plug in for the a and the b. There could be variables in there, there could be numbers in there. As long as we can write each piece as a square, we could clearly factor it this way. That's what our example has shown us. So let's look at some more examples here. Where we need to use this method to factor. So, first example. We want to see something that is a difference of two squares. So, for example, 9x squared minus 49y squared. We notice, can this be written as a difference of two squares? Well, the first piece, the first term can be written as 3x, the whole thing squared. And the second term can be written as 7y, the whole thing squared. So this is a difference of two squares. And so each thing that's being squared we're going to write out. 3x plus 7y, and then 3x minus 7y, because that's the pattern. In this pattern, the 3x is like our a, and the 7y is like our b. So we factored it just by using that pattern. Let's try another example. What about x to the fourth minus 16? You know, initially that x to the fourth doesn't look like a square, but we can rewrite it as a square, right? Because x to the fourth can be rewritten as x squared squared. And 16 can be rewritten as 4 squared. So we can actually rewrite this so that our a here is x squared and our b here is 4. So we could rewrite this as x squared plus 4 times x squared minus 4. In fact, you may notice something at this step. This is a correct factoring. This is good so far. But notice we have something that we could factor even further. Notice this is also a difference of squares. So we could repeat what we just did. The x squared plus 4 is not a difference of squares, but this x squared minus 4 could be rewritten as x squared minus 2 squared. So we could rewrite this as x plus 2 times x minus 2. And now we've really factored it. We've used the difference of squares 2 times. So notice that's a key thing here. Even though this doesn't look like a square, this can be rewritten as a square. And that's what's important, even though it doesn't look like it initially. So, something we may want to note. Whenever we have a polynomial that has only 2 terms, and we're trying to factor it, it makes sense to look and see, are those 2 terms, is it a difference of squares? Because you notice difference of squares always has 2 terms. So that's a good thing to check. Whenever we want to factor a polynomial that has 2 terms, first it always makes sense, of course, to check to see if you can pull any greatest common factors out, but the next thing we want to check is to see if it is a difference of squares, or can be rewritten as a difference of squares. Important thing to keep in mind. Something else I want to note. Notice the sum of squares is different from the difference of squares. A squared plus b squared can't necessarily be factored. Now you may be tempted to say, well, maybe a plus b times a plus b would get you a squared plus b squared. But you'll find if you multiply it out, what you'll actually get is, you get a times a plus b, right? Plus b times a plus b. And as you do that, you'll get a times a plus a times b plus b times a plus b times b. And what is that? That's a squared plus ab plus ab plus b squared. Well, notice these two don't cancel, so you can't get a sum of squares. You're going to get this term in the middle that's not going to go away. You're going to get a squared plus 2ab plus b squared. So as soon as you see something like this, you can factor it this way. But a sum of squares, you can't factor that way. In fact, you can't really factor sum of squares unless you allow yourself to use things that are not integers. So don't make that mistake of trying to factor sums of squares the same way we factor differences of squares. The whole reason the differences of squares works is because when we multiply things with opposite signs, this middle term here will cancel. But when everything is positive, these two terms are not going to have opposite signs, so they won't cancel. So beware the sum of squares. You can't factor them like differences of squares. Okay. We've looked at really all the things that can happen when we multiply a monomial by some polynomials. And we've looked at what can happen when we multiply two binomials. Most of the things that we're going to want to factor are going to fall into those categories. There are a few other patterns that we'll go ahead and point out because you'll occasionally need to use them. For example, there is a sum of cubes pattern, which is just what it sounds like. A cubed plus b cubed. That turns out can actually be written as a plus b times a squared minus ab plus b squared. You can check that out by multiplying these two terms out, and you'll see that you do in fact get this. There's also a difference of cubes. So a cubed, a cubed minus b cubed can be written as a minus b times a squared plus ab plus b squared. You can check that this is true by multiplying out the right side of each of these equations. And you'll see you will get what's on the left side. That way you can assure yourself that these patterns are really true. You know, if we wanted to do a quick example of something, if I had 8x cubed minus 27y to the 6th, I could write this as a difference of cubes. How? Well, 8x cubed is really 2x, the whole thing cubed, minus 27y to the 6th. Well, that's really 27 can be rewritten as 3 cubed, and y to the 6th can be rewritten as y squared cubed. Right? Just 3 cubed is 27. Y squared cubed is y to the 6th. So we could factor this by noticing that in this case our a is equal to 2x and our b is equal to 3y squared, and using this difference of cubes pattern. So I would just say 2x minus 3y squared times 2x squared, so I would need to go ahead and square that, plus 2x times 3y squared, I need to multiply those two together, plus 3y squared squared. So I have 2x minus 3y squared, and then I want to simplify everything that's over here. So 2x squared is going to be 4x squared, plus 2 times 3 is 6, and then I have xy squared, plus 3 squared is 9, and y squared squared is y to the 4th. So I factored it just by using this particular pattern. Okay, so we know a bunch of techniques for factoring. Let's even review them. These aren't all the possible techniques that there are, but these are the ones that we're going to encounter for the kinds of things that we will typically need to factor. So let's remind ourselves what they were. One technique was to find the greatest common factor and pull it out of each term. This is a good thing to try first, because it's easy. We have factoring by grouping. Where we group the first two together and the second two together, and then we pull the greatest common factor out of the first group and out of the second group and hope that what we get in the parentheses are the same. If they are, then we can go ahead and add the coefficients and we're done. The things to keep in mind here are if it doesn't work with the first grouping that we choose, we may need to pick a different grouping. So we may need to rearrange the terms and try a different grouping. We also notice that this is a good thing to try. If we have 4 terms, because that's exactly what we need in order to group the first two together and the last two together. Another technique we know is factoring using the AC method. That's what we use when the polynomial has the form ax squared plus bx plus c, or when we can rewrite it in this form. And in that case, we need to find two numbers that add up to b, but multiply to get us a times c. Right? It's obvious that we want to try that whenever we have anything that can be put into this form. And then, of course, we have factoring using the difference of squares difference of cubes, or sum of cubes. Basically, if anything looks like a squared minus b squared, or if it can be rewritten to have that form, a cubed minus b cubed, or if it can be rewritten to have that form, or a cubed plus b cubed, if it can be rewritten to have that form. We want to look to see if it has one of these three patterns. Remember that a squared plus b squared is not one of these forms. So we might want to note these are good patterns to look for when the polynomial has two terms, obviously, because each of these patterns have two terms. Likewise, up here, this is a good pattern to look for when the polynomial has three terms. Okay, so now that we've summarized our various techniques, let's finish up by trying out some examples where we have to figure out which technique should we use. And actually I should say techniques, because sometimes we need to use more than one. So let's look at example 1. What about this? 12x cubed minus 27x. Well, the very first thing we always want to look for is, can we pull out any greatest common factors? So let's look at this one. Is there any greatest common factor that we can pull out of both the first and the second term? Well, I notice right away both terms have x's in them, so I know I can pull out an x. So let's think about greatest common factors. So I know I can pull out an x. Anything else? Well, 12 and 27, it looks like 3 goes into each of those. 3 times 4 equals 12, 3 times 9 equals 27, so I could pull out a 3x, in fact. So I'm going to do that first. And in fact, I'll even rewrite it as addition first. 12x cubed plus negative 27x. And now pulling out the greatest common factor of 3x, what do I have left? Well, 12 divided by 3 is 4, and x cubed divided by x is x squared, plus negative 27 divided by 3 is 9, and x divided by x is just 1, so this is what I get. Alright, I've used the greatest common factor method. That's one technique. But now I have to ask myself, can I factor this any further? We notice that here, in the parentheses, I'm left with a polynomial with two terms. So here's a good time for me to ask myself, could this possibly be a difference of squares, a difference of cubes, or a sum of cubes? Well, it's a difference because I notice there's a negative sign right there. And so could it be a difference of squares or a difference of cubes? Well, in fact, 4x squared, that's a square. If I square 2x, I get 4x squared. And 9, that's a square. That's 3 squared. So I can rewrite this as 2x, the whole thing squared, plus negative or minus, if I want to change it to a minus here, 3 squared. So that's a difference of squares. So I can go ahead and use the pattern for difference of squares to write this as 2x plus 3, 2x minus 3. So I use the technique that this was a difference of squares. So here I had to use two different techniques. I had to look for a greatest common factor, and I had to look for differences of squares. But once I did that, I was able to go ahead and factor this completely. There's no further factoring that can be done. Let's look at another example. In this example, I have x cubed minus 4x squared minus 9x plus 36. Okay, so since this example has 4 terms, it makes sense for me to try factoring by grouping. So I'm going to try that. First thing I'll do, though, is write it out as addition. So x cubed plus negative 4x squared plus negative 9x plus 36. And now let me try grouping it. I'll group the first 2 together, and I'll group the last 2 together. We'll see if that works. If that doesn't work, I'll try rearranging it and doing a different grouping. So, what's the greatest common factor in this grouping? Well, x squared is the greatest common factor. And in this grouping, what's the greatest common factor? In this grouping, it looks like 9 is the greatest common factor. Alright, so let me go ahead and use that to rewrite this. If I factor out an x squared, what's left over? Well, x cubed divided by x squared is just x. And negative 4x squared divided by x squared is just negative 4. Here, if I pull out a 9, negative 9x divided by 9 is negative x. And 36 divided by 9 is 4. Now, I need to check. Are the 2 things in the parentheses the same? They're almost the same, but not quite. Over here I have x plus negative 4, and over here I have negative x plus 4. I notice these are almost the same, right? Notice that x plus negative 4 and negative x plus 4, all I need to do to get from one to the other is multiply or divide by negative 1. Notice x times negative 4, if we multiply it times a negative 1, is equal to negative x plus 4. Because if I distribute that negative 1, I get exactly this. So, if I think back, here's what I may want to do. Here, I took out a greatest common factor of 9. But what if instead I took out a negative 9? What would that have done? Well, if I did that, I would instead get, this part stays the same. But if I took out a negative 9 over here, negative 9x divided by negative 9 is positive x. And 36 divided by negative 9 is negative 4. Now these 2 parts are equal. So now I can go back to simply adding the coefficients. So I'll get x squared plus negative 9 times x plus negative 4. So I've factored by grouping. But wait a minute, is that all the factoring I can do? Can I do anything further? Well, you may notice that actually this looks like a difference of squares again. So in fact, I have a bit more work to do. I can rewrite this one as x squared minus 3 squared, and this is still x plus negative 4, or I can write it as x minus 4, if that's simpler. And so this can be written as x plus 3, x minus 3, and then we still have x minus 4. So we've finally factored it as much as we possibly can. We used 2 techniques here. Here we used factoring by grouping, and we noticed we had to be careful about the negative signs to make these come out the same. And then here we used difference of squares. Let's try a few more examples. We have 2x squared plus 4x minus 30. I'm going to go ahead and rewrite that as all addition. 2x squared plus 4x plus negative 30. So which technique should we use here? Well, we notice this is in the form ax squared. Ax squared plus bx plus c. Here our a is 2, our b is 4, and our c is negative 30. So we know we need to find 2 numbers that add to get 4 and multiply to get 2 times negative 30, which is going to be negative 60. Okay, so What are the factors of negative 60? Well, we could do 2 times 30, but negative 2 and positive 30, or positive 2 and negative 30 are never going to add together to get 4. We're going to need numbers that are a bit closer together, so I might try bigger numbers. 6 goes into 60, so I could do negative 6 and 10, or 6 and negative 10, and in fact, what is 6 plus negative 10? That's negative 4, but I want positive 4, so that won't work. But negative 6 plus 10 is going to give me positive 4. And I already know that negative 6 times 10 equals negative 60. So I've found the two numbers I want. So I can go ahead and rewrite this. I can write 2x squared plus 4x plus negative 30. That can be rewritten as 2x squared plus negative 6 plus 10 times x plus negative 30. And so now I've broken my b down into the two pieces like I need. I have 2x squared plus negative 6x plus 10x plus negative 30. Now I'm ready to go ahead and factor by grouping. I group the first two together and the last two together. The greatest common factor here is 2x. And the greatest common factor here is 10. So now we try rewriting it that way. If I pull a 2x out of this first group, 2x squared divided by 2x is x. Negative 6x divided by 2x is negative 3. 10x divided by 10 is just x. And negative 30 divided by x is just negative 3. So I need to double check. Are these two bits exactly the same? And in fact they are. They're equal. So that's excellent. Now I can just add the two coefficients. So now I get 2x plus 10 times x plus negative 3. And I can't factor that any further. So I'm done with that one. Let's do one final example. 3x to the 4th plus 18x squared plus 27. Alright. First thing I'm going to look for, is there a greatest common factor I can pull out? If there is, it'll make my life easier if I do it at the beginning. In fact, here I do have a greatest common factor. I can pull 3 out of each piece. So, not a lot, but it's something, so let's go ahead and do that. If I pull a 3 out front, 3x to the 4th divided by 3 is just x to the 4th. 18x squared divided by 3 is 6x squared. And 27 divided by 3 is 9. So I've simplified it somewhat. But now I need to ask myself, can I do anything to factor this further? Well, I notice that this has 3 terms. So I might want to ask myself, can I rewrite x to the 4th plus 6x squared plus 9 in the form ax squared plus bx plus c? Is that possible? Well, let's try it. So I've got 3x to the 4th plus 6x squared plus 9. Is there a way to write that inner part? Well, how could I write x to the 4th as a something squared? Well, I could write it as x squared squared. And 6x squared I could rewrite as just 6 times x squared. And then 9 still works. This is a little confusing because we've got x here. Maybe it would help if instead of using the form x, we could write the letter y in that place. Remember that the x in this particular form is really just an empty box. So notice here, if we let x squared be equal to y, then we've got that form. Here's our y, here it is again, something squared plus 6 times that something plus 9. It does in fact have this form. We're able to rewrite this so that it looks like that. So now we can actually use our technique. If it helps, you could even rewrite it like this. You could even rewrite it as 3 times y squared plus 6y plus 9. And solve for y, but just remember at the end you would need to substitute y equals x squared. You have to put an x squared in for y every time at the end. But if we do this, we could do this, right? In this case, it's like we have a 1 out front. So if we do this in this form, our a is 1, our b is 6, and our c is 9. So we need two numbers that add to get 6 and multiply to get 1 times 9, which is just 9. Well, we may even be able to do that without actually having to write out all the factors. If you think about it for a moment, you can think, okay, 3 times 3 is 9, 3 plus 3 is 6. So 3 and 3. These will work, because 3 plus 3 equals 6, and 3 times 3 equals 9. So, let's rewrite this. We still have that 3 hanging out front, and then we have x squared squared plus, and that 6 can now be rewritten as 3 plus 3 times x squared plus 9. So we can rewrite it (3) x squared plus 3 x squared plus 9. And you'll notice at this point we've broken it up into 4 pieces. We can now do factoring by grouping. So if we want now, we don't have to keep rewriting it as x squared squared. We can just write it as x to the 4th plus 3x squared plus 3x squared plus 9. We were just using that format in order to be able to see that we can use this particular technique. Okay, so now we can go ahead and do factoring by grouping. Group the first two together, group the last two together. The greatest common factor here is x squared. The greatest common factor here is 3. So let's go ahead and factor that. So this will be x squared out front. X to the 4th divided by x squared is x squared. 3x squared divided by x squared is 3. Here we pulled out a 3, so 3x squared divided by 3 is just x squared. 9 divided by 3 is 3. And so we have to check, are the two variable parts that are left over here equal? They are in fact equal, so this is good. Check. We can now add the two coefficients. So our final step here is to add the two coefficients, x squared plus 3 times x squared plus 3. We notice you might be tempted to try to factor each piece, but these are sums of squares, and in fact the 3 isn't even a square unless you're going to allow yourself to use numbers that aren't integers anymore, so we can't actually factor this any further. We're all done at this point. So this last example was more complicated because we had to use some different techniques, and we had to rewrite x to the 4th and x squared a little bit in order to make it look like it's in this form. But even in this case, we were able to use the 3 basic techniques that we have in order to recognize the patterns that are going on and in order to be able to factor this trinomial. Okay, so now you should be all set to go ahead and try some of this factoring on your own. You should be able to do the homework in this section where you practice factoring all kinds of polynomials.